So we've got this little torque question, and what I want to actually do is just kind of check in and talk about a few of the ideas that help us set up this problem. So we did a lab last time where we hung rulers, if you remember, and we bounced different masses off the rulers, and we actually drew some conclusions about the nature of how we get things rotating in the first place. And what we realized is that if we want to get an object rotating around a pivot, um, the rotational analog to force that gets it rotating depends on, well, the force itself, and also the distance from the pivot point. And not only that, and we don't go into so much detail in an introductory physics class, but we need that distance. We need that. We need the what we call the lever arm, and the force to be perpendicular to each other, or rather, that part of the force which is perpendicular to the lever arm is what has the effect of making it rotate. Now, continuing with this simple idea, we wanted to make things a little bit more interesting by studying a real system. And the system we studied is one of a solid sphere that is dropping and rolling and hitting the ground. So, to be clear, let's do what's called an extended free body diagram. So, we're no longer going to treat this as a mass. We have a tension force going up from the string. We have the weight force, Fg, pointing down. And let's talk about the effect of these forces. It turns out we have two things going on. We have the net force making the sphere accelerate, and we have the torque making the moment of inertia rotate and gain speed. So this is the torque equation, and this is the force equation. They're analogs to each other, meaning just as force makes the mass accelerate, torque makes the moment of inertia spin faster and faster and faster. So we call that angular acceleration. Couple of other ideas. Let's be clear. This weight is unable to apply a torque to get it spinning. It's only the tension that gets it spinning. And we're going to define up as positive and down as negative. So here's the idea. We have the tension force acting upwards. It opposes the weight. And the effect is that the mass accelerates downwards, hence the negative sign. Now, the other thing that we have to account for, this torque is a result of the tension force. Just as we wrote R cross F from our lab work yesterday, we have R, the radius, okay, as the lever arm, and T coming together to sort of produce that torque, for lack of a better way of saying it. And the effect is that this moment of inertia undergoes angular acceleration. Now, yesterday we dealt with the idea that omega is the angular speed divided by the radius. Well, we have an analog to acceleration called angular acceleration. An analog means that it's the thing that does acceleration for spinning rather than just plain old moving. So the angular acceleration is the acceleration that we have here divided by the radius. Okay? So the moment of inertia is given here as 2/5 times m r squared times alpha, which is a over r. So this part here is the r perpendicular cross f part. This is the I, and here I'm just substituting in for alpha. Now we're going to simplify a little bit. So we've got tension minus 0.2 times 10 equals 0.2 times negative a. That's going to be t minus 2 equals negative 0.2 times a. Here, we have the radius is 0.2 meters. So I'll have 0.2 times the tension equals 2/5 times m, which is 0.2, times r squared. When I square that r, that's going to be 0.04, 0.2 squared, times a divided by 0.2. Let's cancel a couple of things here. This will cancel with that. Continuing, 0.2 times t equals, I'm going to convert 2/5 to 0.4 times 0.04 times a, divide by 0.2. This is going to give me t equals 2 times 0.04a. T equals, 0. And that's going to be 0.08 times a. So let's do a little substitution. This is equation 1, this is equation 2, and we can substitute. So we have t minus 2, 0.08a minus 2 equals negative 0.2 times a. I'm going to rearrange a little bit. I'm going to add plus 0.2 to both sides, 0.2a to both sides. That's going to give me 0.28a minus 2 equals 0. Let's add 2 to both sides. So I'm going to get 0.28 times a equals 2. I'm going to isolate a by dividing. So a equals 2 divided by 0.28. And when I go ahead and solve, I'm going to end up getting a equal to I'm getting 7.14 meters per second squared. So there we go. All right. So that is the torque question. And I will actually go ahead and upload part 4 right